Hello and welcome to EECraft. In this video, we will explore the power of the PIO blocks and examine the benefits of state machine executions that are independent of the main processor core. We will also review a simple PIO code to understand its structure and discuss a few useful functions for integrating the PIO code into an Arduino sketch. If you are new to the PIOs of RP2040, I would recommend watching one more video about installing the necessary tools and building the first executables using the Arduino IDE and a couple of other software tools. The link to that video is posted in the description box. In this video, we will create a program that blinks an LED using a PIO state machine instead of the delay function. The Raspberry Pi organization has shared the PIO Blink program on their GitHub page, which we will use in this tutorial. Additionally, we will go through the program step by step to understand how it works. This will enable us to modify or change it as needed. The highlighted section contains a program written in the PIO assembly language. The code begins with a .program statement, and the program identifier is set to blink. It is important to follow this format, which will be used during the compilation and linking process. In the code, the value stored in the TX FIFO by the application program is first pulled into the OSR. After that, all the 32 bits of that value are shifted out to the register Y. Please ignore the RP2040 for now. In the next line, the value of the register Y is moved to the register X. Following this, the pins are set to 1 or the signals are driven high. The program will then keep jumping to the same label LP1 until the scratch register X is non-zero before decrementing. This step adds a delay in the program. In line number 17, the 32-bit value stored in the scratch register Y is moved once again to X. After that, the pins are set to 0, which drives the signal on the assigned pins to low. The counter is then set up again by decrementing the scratch register X in a loop and using a conditional jump statement. So far, this just sounded simple, isn't it? The RP_target and wrap statements are directives to repeatedly run the section of the program within. Without the wrap directive statements, the entire state machine program will get repeatedly executed, which is not desired here. The code has a section starting at line 24 and ending at line 34, which is the CSDK binding. This function is utilized by the PIOasm tool to transform the assembly program into a C++ program. It helps the user instantiate an instance of the PIO Blink program within the Arduino sketch. The naming conventions are required to be adhered to generate an error-free code. Note the use of the program identifier. This function configures the state machine, assigns the output pin, and passes the 32-bit count value for the delay. Let's copy the code to the project directory and convert blinked PIO file to blink.pio.h using PIOasm program. In order to run the PIOasm executable, we must first open the command prompt and navigate to the path inside the build directory where the PIOasm exe file is stored. After that, we need to provide the source path, PIO file, and indicate the destination path for the C++ header file that will be generated. Let's create an Arduino sketch in the same folder as the PIO header file. Here I have saved the sketch used in the previous video to start with. Next, I am going to modify the sketch to incorporate the PIO Blink program. First, I need to include the blink.pio.header file just created. I have also included the pio.h file. Next, a PIO object is created and PIO0 is assigned to it. Next, a PIO object is created and PIO0 is assigned to it. In the setup function, the PIO program offset is loaded in PIO's 5-bit program address space. In the following line of the sketch, a free state machine on a PIO instance is claimed, and the PIO program is initiated with the built-in LED pin assigned to the state machine pin. In the next line, the state machine is enabled. A 32-bit integer value specifying the number of wait cycles is passed to the TX FIFO in the final statement of the setup function. Let's also add the blink program, available as an example sketch. We will set the GPIO28 as output to drive an LED on the breakout board. The LED will blink on and off at an interval using the delay function. This LED will help us in experimenting by changing the delay in the loop function to check if that has any impact on the PIO operation. Please note that the PIO function driving the built-in LED on the Pico board is controlled by the GPIO25. Next, we will finish by doing a few quick housekeeping to define constants for the delays, so that readability is easy. In this program, we will be running the RP2040 controller to the maximum frequency of 133 MHz. That means, in 1 second, there will be 133 million clock cycles. Therefore, to provide a delay for the X scratch register to get empty in 1 second, it should start with an initial value 133 million. We have prepared the sketch and are ready to upload it to the RP2040 Pico board. Let's upload it and observe both LEDs. Note that the Pico board is connected to the COM port and the frequency is correctly set at 133 MHz. We could observe that the onboard green LED and the blue LED on the breakout board are blinking on and off every second in unison. Let's conduct a simple experiment. I will increase the delay value inside the loop function. This will result in the blue LED, which is driven by the application program, slowing down. However, the onboard green LED, which is driven by the PIO program, will not be affected. Let's observe after the sketch is uploaded. Okay. We could observe that the PIO program is not affected by the delay introduced in the application program, as the PIO state machines are more or less independent. Let's try another value and increase the delay in the loop function further. The delay in the loop function simulates the increased execution time of a larger application. When this program is uploaded, we will still see the PIO program blinking the LED at the same rate as earlier. Please consider subscribing to our channel if you enjoyed this tutorial. In our next video, we'll delve deeper into the capabilities of PIO for RP2040. Thank you for watching, and we'll see you soon.